All right, welcome back. Next up is 1.2, our piecewise functions. We're not going to be looking to graph these things. We're just going to be looking at simply evaluating them and then talking about the idea of whether or not a piecewise function is continuous. So piecewise functions look like this right here. We have this curly bracket around these different types of functions. They could easily be all different types. Like I have here, linear, quadratic, and square root. They could all be linear, all quadratic, all square. It just doesn't really matter. The key is there can be different functions with their own unique domains. And the domain is where what's important to look at, because like the 3x minus 4 is where x is less than or equal to negative 5. The 2x squared minus 5 is in between negative 5 and negative 1. And then the square of x plus 1 minus 4 is when we're bigger than negative 1. So we have to make sure we're part of the relevant portions of that domain. If I'm talking about x equals 2, I'm only concerned with the square root. It doesn't go to the linear or the quadratic. Or if I'm talking about when x equals negative 3, I'm only caring about the quadratic. Or x equals negative 7, I'm only caring about that linear. So it just kind of depends on which one we're referring to. And that's the idea. So we want to evaluate it. We're subject to the correct portion. Pay attention to where it would fit for those inequalities. Watch out for that pointed transition. If I go back a second, that's at negative 5 and negative 1 where we go from linear to quadratic or quadratic to square roots. So pay attention to where the equal to is. That tells you which one they plug into because you can't plug into them both. So we want to find these 5 different values, f of 1 through f of negative 5, 8, negative 4, and 3. Well, f of 1, recognizing x equals 1 would fall in between negative 4 and positive 3. So therefore it will be 6 times 1 plus 2, which gets us 8. F of negative 5 is less than negative 4. So we'll go to the quadratic there, which again, that's a negative 1 times the negative 5 squared plus 2 times negative 5 minus 3, giving us negative 25 minus 10 minus 3, so that would be a negative 38. All right, so again, negative x squared, remember it's negative 1 times x squared, so you can probably evaluate that part there. Part C wants f of 8, so f of 8 would clearly fall, it's bigger than 3, so it would fall with that square root, so it would be the square root of 8 minus 3, which is the square root of 5. If we could simplify the square root, we would. If it was perfect, obviously we would say what that value is. But since it's neither of those things, it's just an irrational square root, we leave it alone. Don't give me a decimal for this kind of stuff. Simplify it if it's possible. Like if I got square root of 12, tell me 2 square root of 3. But otherwise, don't give me decimals there. So what you got to watch out for, obviously, is where we have the points of transition. So for D, f of negative 4, we got to pay attention to where the negative 4 will go. Because there's 2 negative 4s in the problem. The top one for the quadratic, the middle one for the linear. It's all about where is that equal to. And the equal to is part of the linear, so we're going to do 6 times negative 4, and then plus our 2. So that's going to give us negative 24 plus 2, which is negative 22. And then f of 3, well, that's going to go to, again, where there's the equal to. That's this one right here. So it goes to the bottom to the square root. So it's the square root of 3 minus 3, which is square root of 0, which is just simply 0. So again, when it comes to evaluating the piecewise function, and again, there could be 2 pieces to it. That's the minimum number. That's part of the piecewise function. There could be 3, 4, 5, 6. There could be as many parts as we want to each of these functions. Just make sure you're substituting to the correct portion when you're going to get your particular value. Watch out for the inequality signs. Watch out for the equal to's. Now, the second element for what we're talking about with our piecewise function, the idea of whether or not it is continuous. So a continuous piecewise function meets 2 criteria. All the functions that make up the piecewise function are individually continuous, and at each point in a transition, the value of both functions before and after are the same. So criteria number 1 is going to pretty much be satisfied by almost everything we're going to do. That would only really not be satisfied if we were talking about rational functions as part of this, where a rational function would have a vertical asymptote and therefore not be fully continuous. But if it's a linear, it's a quadratic, even if it's a square roots are technically continuous everywhere that it actually exists. It doesn't exist at certain points because of the whole square of a negative number, but it doesn't make it not continuous. So the thing we're really going to have to really just focus on is point 2. At each point of transition, the value of both function before and after are the same. And that's done very simply. All we do is we take this point of transition, we plug it into both equations, and we see do we get the same equal value. And we work through it, and we can see that in this particular case, they're both equal to 11. Therefore, yes, this is a continuous function. Because if the point of transition is shared by top and bottom, even though technically the top linear 2x plus 1 would never actually equal 5, it has to be less than 5, not equal to it. It just means it ends there. Because like if you remember when we were graphing this thing, you were just doing an open circle at that ending location. Because it would not be practical to attempt to try and find the value for when, like, x is 4.999999999 kind of thing. Because you could still go further than that. So you just find out what's happening at 5 and do an open circle. Here, you can clearly see they would be ending at the same spot the other one begins, so they are continuous then. They're sharing that point of transition. For this one, we're substituting -2 into this. So it's -3 times -2 plus 4, and then -1 times -2 squared. Remember, -x squared is -1 times x squared. We get +6 plus 4. We get -4 plus 6, because the -2 squared is 4, but times -1 is -4. As you can clearly see, 10 does not equal 2, so this one is not continuous. All right, so that's all we're looking to do with the idea of whether a function is continuous or not. And if we had a 3-parter piecewise function, then you would just do for the first part, to have that shared inequality, and then for the second part, their shared number. You look at that situation. All right, so that's it for our piecewise functions. Again, like I said, we're not graphing here. The goal, you should be comfortable with the idea of graphing from Algebra 1 and Algebra 2. So we're not taking a look at that here. We're just looking at just the evaluating and the continuous aspect of it. The idea of things being continuous we'll discuss a bit more throughout this year and next year in calculus. So make sure you're comfortable with the grasp of what that is. All right, next up is our inverse functions. So I'll see you next time for that one.